Okay, so what we're thinking about in this class is fundamental mathematical questions. And so let me ask this in a way that won't look like it's even remotely related to algorithms, but it actually ends up getting at some of the core fundamental mathematical principles that we care about in this class. Okay, so let me draw you two shapes. The first shape is going to be a line. Right? It's a line, and I'll call this a line of dimension 3. So the length of a side on this line is 3. So there's my line. Whoops. And let me draw you a grid. That's my second shape. And this grid will be also dimension 3. Right? So the length of a side of the grid is 3. So I'll say they're both dimension 3. And so we could ask this question, and this is just a question of geometry almost. The question is, how many dots are in a line or a grid of dimension n? In shape of dimension 3. Not just 3, dimension n. Right? And you don't have to think very long to know, right? The answers are very simple for the line, and I'm gonna write this as CL of n. So CL of n. So for the line, if the dimension is 3, there's 3 dots. If the dimension is 6, there's 6 dots, and so on. Right? There's exactly n dots in a line of dimension n. Okay, and for the grid, it's equally easy to think about. Oh, let me just make sure that this is clear. So CL here, this is the number of dots, and then n, this is the dimension. So for the line, it's n. For the grid, it's for the grid CG, g of n, it's n squared. Right? And that's clear because this is a square, right? And it's a square of with a side of length n. So how many dots are there? Well, it's equal to the area of the square, however you want to put it. Sorry about that little flip in the screen. Okay, so now let me ask a similar question to what I asked about the algorithm, but now I'll ask it for the line and the grid. So basically, I'll ask how sensitive the number of dots in these two things are to their dimension. Okay, so here's my question, and I'm going to ask this in the mathematical way that I asked it for the algorithm. The question is, what is the limit as n approaches infinity of CL of 2n divided by CL of n? Right, what I'm asking here is, if the length of the line doubles, how does that affect the number of dots in the line? This is easy to work out, right? So this is something I can just work out directly. I don't have to write some complicated proof for. I can just work this out directly. So this is just equal to the limit as n approaches infinity of 2n over n, right? So a line that has 2n dots in it, or sorry, a line of dimension 2n has 2n dots in it, and a line of dimension n has n dots in it. This is simple. The n's cancel, right? They're both greater than 0, so you can just divide them. So the n's cancel, and we just end up with the limit as n approaches infinity of 2, which is just 2, right? And so there's our answer, right? How does the length of a line, how does the number of dots in a line change if we double the length? The number of dots doubles, right? So number of dots doubles. All right, so let me ask the question for the grid. And nothing here should be too surprising, right? This is all stuff that you should have a strong intuition for to begin with. We're just working it out in detail to make sure that the mathematics are clear. So the question here is the same now except for we're going to ask it for the grid. So what is CG of 2n divided by CG of n? What happens to the number of dots in a grid if its dimension doubles? Well, we can plug in expressions. So this is the limit as n approaches infinity of 2n squared. So I just plugged 2n into n squared divided by n squared. If there's anything in here where you're like, ooh, I don't know why that happened, you have to pause the video and work it out for yourself, figure out why it happened. And if you can't figure out why it happened, make a note of it, and then in our synchronous sessions, talk to me about it. Ask me the question, right? Because everything here needs to be clear, right? There can't be anything that I say here that goes over your head and you just let it go over your head. You've got to chase these things down. Okay, so here's what I've done. Well, what do we do when we want to raise a power like this? We just apply the power to everything in here. So this is the limit as n approaches infinity of now 4n squared over n squared. What happens? My n squareds cancel just as the n's canceled before, and I'm left with 4. Pardon my weirdness there. 4. So what's the answer for the grid? Well, if I double the dimension of the grid, so double the length of a side, essentially, I quadruple the number of dots, right? So the number of dots quadruples. Okay. So this means that the grid has a different, we'll call this order of growth. The grid has a different order of growth than the line. Okay. So everything here should be relatively elementary, right? But now I want to ask a new question. I want to ask, what if instead of a line or a grid where the expressions are really simple, what if we were asking the question about a triangle? Question, what about this shape? Right. So I'll call this the triangle. And I can ask the same question, right? How does the number of dots in a triangle change as the dimension of the triangle changes? And so I can ask, mathematically speaking, I can say, so the triangle has this t. Am I using t? I am using c. So I'll use c t of n. So first I have to ask how many dots are there in a triangle of dimension n. But then I have to ask, how does this change? How does the number of dots change as I change n? So again, what is the limit as n approaches infinity of ct of 2n over ct of n? And here's a way I can ask this question. And this question is not something that you would have known even what to do with until just now, having seen the line in the grid. I can ask, is the triangle more like a line or is it more like a grid? Right, so is triangle like line or grid? Right. Now to answer this question completely, we do have to work out all these expressions here. Right? We actually need to have ct of n kind of completely clearly defined. And so once we get that answer, we'll attack this question formally. But this is a surprisingly algorithmic question. Right? We'll often be asking questions that mathematically end up being precisely this, where we essentially ask, is this shape that we've just discovered, where the shape has some resemblance to an algorithm, is this shape more like a line or more like a grid? All right. So stay tuned for the next lecture to figure this out.